Hi, ladies and gents. Let's talk a little bit about the sun and how the solar system was formed. And primarily, we're going to start in this video talking about the formation of the solar system. So how did the solar system come to be? And basically, how do all solar systems form? Well, and also the question is, how do we know all this? Prior to 1992 and our observational tools, we were limited to trying to figure out the story of our solar system by only looking at our solar system. Since 1992, we have been able to see thousands of other exoplanets. These are planets that are orbiting other stars out there in the galaxy. And these other solar systems have given us massive amounts of information about how any solar system is going to form. So we're getting this story better, more finely tuned all the time. But one of the basic things that we do in astronomy all the time, I call it a life in a day. We're trying to look at things that have taken billions and billions of years, and how in the world, in a mere human lifespan of, let's say, 80 years for a human to live, can a scientist figure out how something occurs that took billions and billions of years? Well, let's use this analogy. Let's say a little spaceman comes to Earth, and on the day that this little space creature comes to Earth, he's only here for one 24-hour day. Well, one 24-hour day is not enough time to really see the entire human lifespan. But during that one 24-hour day, he's going to see ladies who are expecting, small children and babies, young adults, families, people who are a little older, people who are very old, and then he's going to see death. By piecing all of these pictures together, you can put together the path that a typical human takes from birth to demise. We do the same thing with stars. In our mere little human lifetime, we look at all sorts of different stars, lots of different solar systems, and we see them at different stages of life. And then we try and piece all of that information together to give us a lifespan. We think our solar system is about 4.6 billion years old, based on radiocarbon dating, based on a whole bunch of different things. But when we dated rocks from the moon rocks are about 4.4 billion years old. Meteorites, we have found some that are 4.56 billion years old. And so our solar system can only be as old as the materials that make it up. And if the things that make up the solar system are about 4.6 billion years old, then that's how old it is. The universe in total, we believe, is 13.7 billion years old. And so we suspect that our solar system is a second generation, that you and I and the stars and the planets actually were part of other stars and other star systems before we got recycled into our current world. So how do you start building a solar system? You have to have a collection of raw materials, and the places where the raw materials hang out are called nebula. Nebula are these combinations of gas and dust. If you see pictures of nebula and there are dark patches, those dark patches are dust. Why is that dust important? These are the heavy elements, calcium, oxygen, nitrogen, carbon, that make up you and me and planets. The gases make up a lot of a nebula, but those gases, hydrogen, helium, nitrogen, some nitrogen as well, these gases actually make up most of the stars. And so you have to have a combination of all of these to begin. Something makes that cloud of dust, that is a nebula, begin to collapse. Astronomers are still trying to figure this one out. It is either some sort of a gravitational effect or some sort of a shock wave. Now, gravitational effects are pretty simple. You have one dust particle and another dust particle, and they are mutually attracted by gravity to make a bigger dust particle. Then this particle collects or attracts another one, making a bigger dust particle. And over time, this slow process occurs to get bigger and bigger things, so you end up with planets and stars. Some astronomers believe that gravity, with the aid of some sort of a shock wave that makes particles kind of push together, kind of causes the creation of a solar system. What kind of thing could cause this sort of shock wave? Well, it could be something like a gravity wave. Gravity waves are created when you have large gravitational events like two black holes that actually collide. This will actually ripple the fabric of space and making particles get squished together. Some of these shock waves can be due to things like supernova, and supernova are explosions of stars. Whatever the original source, we believe it is a combination of both that caused this original nebula to begin to collapse. Now, almost everything in the universe has got rotation. There's some sort of rotational or spinning motion to it. And we've talked about this conservation of angular momentum. This is a big rule of physics, a big rule of science. And it says that anything rotating wants to keep rotating. So if you start out with a big cloud of dust or gas and it's rotating, it's going to maintain that rotation as it collapses. Things that move towards the center are going to speed up, like the ice skater pulling her arms in, and things on the outside edge are going to spin slower. The process of rotation and spinning also is going to make this big ball of an object flatten out into a disk. It has to do with the torques on all the particles involved. What is produced is an accretion disk. The name of this is an accretion disk, and as always, if it's a new word, that's always fair game for quizzes, etc. Accretion is the process where gravity is going to attract individual particles to make massive objects. That's the name of this process, where you have dust grain plus dust grain gives you bigger dust grain. But over time, this also produces a big spinning disk of dust grains that are being attracted to each other, and this is called an accretion disk. This is a lovely picture because within this accretion disk, this is taken with different wavelengths beyond visible light. But you see this glob and that glob and that glob. These are areas where those dust particles are starting to come together and form something more massive and more dense. Well, that's going to turn into planets. So within the accretion disk itself, there are going to be localized pockets of higher density. These are going to be planetesimals. Planetesimals basically meaning baby planets. These baby planets are going to clump together, making objects that are about 1 kilometer in size, which is a little over half mile in size. And then these individual planetesimals are going to then clump together to make bigger clumps. And it is basically a process of little things clumping together to make bigger things to make bigger things. What we end up with is protoplanets, proto meaning being born or being developed, and these are going to be orbiting a pre- or proto-sun. Now the planets that we are part of, the terrestrial planets, Earth, Venus, Mercury, Mars, these are going to be rocky objects full of iron and oxygen and carbon and a lot calcium and a lot of solids and things like that. And as this accretion disk spins around our little proto-sun, the rocky things that are going to be kind of near that star, they're going to start to clump together, and that's going to form the terrestrial planets. But it's awfully hot near that proto-sun. So hot that we're not going to get an awful lot of gases. There's going to be very few gases that are going to form into a large enough bunch to form planets. Matter of fact, there's a mathematical line in a solar system which is called the snow line, and some books call it the frost line. This is the distance from the star where it is cool enough for gases to become ices. And at these great distances, where all of these things that are gas next to the hot sun can actually be solid particles of ice, that's where you're going to get your gas giant or ice giant planets. And you do need to know this term, frost line or snow line. On our solar system, this is about 3 astronomical units from the sun. And it's just the place where it's cold enough where you're going to get all this ice instead of some hot, hot gas. So our gas giants, when the protosun was being produced, when it was kind of condensing under its own gravity, there was this region of tremendous heat, and the rocks could form into planets there. And it also blew out, due to its solar wind, etc., it blew out lots and lots of this lightweight gas. Well, you push that lightweight gas past that frost line, and past that frost line, this now turns into little icy solids, and the icy solids can then condense, just like particles of dust will, into bigger particles, and then particles condense into bigger things, and eventually you end up with the gas giants. Between Jupiter and Mars, there is the asteroid belt. And the asteroid belt, there are some different debates of why the asteroid belt is there. Some people have said, and some hypotheses, is that that was supposed to be a planet in the asteroid belt, but Jupiter's gravity just kept pushing and pulling on things to prevent that planet from forming. Some hypotheses basically say there was never enough mass in the asteroid belt to make a full-size planet occur. And other hypotheses said, yes, there were all these little planetesimals, all these little bunches, but Jupiter's gravity was just so intense that these things could not condense down to form something bigger. Instead, Jupiter would fling these pieces in all sorts of different directions. It's called clearing the asteroid belt, and when Jupiter cleared the asteroid belt, it got rid of about 96% of the mass that was in that belt, and only about 4% actually remains. So the stuff that was cleared is thrown in all directions. It's thrown some towards the inner solar system, some towards the outer solar system. Where all of that stuff landed, the stuff on the far, far reaches of the solar system make up the Kuiper belt and the Oort cloud. And the rest of it created a period of time of very heavy asteroid bombardment. About 4 billion years ago, okay, the solar system is about 4.5 billion years old. And so when it was about 0.6 billion years old, there was this period of heavy asteroid bombardment, as Jupiter threw and flung all these bits and pieces from the asteroid belt all over the solar system. And you can tell when you start looking at big moon craters, and there are small moon craters inside of the big moon craters, that there was a lot of large debris to begin with, and then smaller debris, and then smaller debris, and then eventually tiny little micrometeorites that we have today. Other things left over from the creation of the solar system got flung to the far reaches, which is that Kuiper belt. That Kuiper belt is out about the distance where Pluto hangs out, and Pluto actually is a Kuiper belt object, and that is a lot of icy, rocky bodies out there. And then things that got strung further, way further out, make that Oort cloud, which is about 1.5 light years away. And this is, we think, the debris. This is like the leftover. If you take a loaf of bread and you slice that loaf of bread with a knife, you're going to get crumbs. And these are sort of the crumbs that are left over from the creation of our solar system. I'm going to ask you to watch a little video kind of going through this, and we're going to come back and we're going to start talking about the sun.